Okay, sir.
Right.
Thank you.
Bismillahirrahmanirrahim. So today we will actually do those parts of chapter 5 which we were stuck in the last lecture, especially concerning a problem that was related to the premium paid by our insurance company provided that the damages were exceeding $400. If you could remember that problem. So in that problem, there were certain mathematics, especially some expectation variables. Actually, I found out that they were very simple. The book actually were using notations that were a little bit different as compared to standard use uh, notation. That is why we were getting a little bit, confused. But I have gone through it and I have also made my notes. So now I think it will be understood very clearly. All right. So it was example 5.4. So we have done all of this. That the expectation of the random variable y, was x minus 400 plus. So y was the amount paid by the company, which will be x, whatever the cost, minus 400 plus was that if it is greater uh, than if it is greater than 400, then you will get that value x minus 400. If it is less than 400, it will give you 0. Right? That was your y. All right. So we also saw that if we know that the y random variable takes values greater than y, then still it will remain exponential with the same mean because of the lack of memory of an exponential process. So the y random variable or the x random variable, that was the damage, and that was an exponential random variable. So x minus 400 will also be exponential. X minus 400 will also be exponential. So I could say that the y random variable for I is equal to 1, I is equal to 1 means that x is greater than 400. So damages will still remain Poisson or exponential with the same mean of 1000. So mean will remain 1000. And expected value when mean is equal to 0. So it means that what will be the value of the random variable when I is 0? When is I 0? I is 0 when x is less than 400. So what will be the expected value of y? Y is x minus 400 plus. It will always be 0 when I is equal to 0. So it will always be 0. Third thing was, what was the variance? So, once I is equal to 1, it is an exponential random variable, and variance is always 1 over lambda square. And here the mean is 1 over lambda, which is 100. So 1 over lambda square will be again 1000 square. So this will be as it is. And variance when I is equal to 0, then always the value of the random variable will be 0. So its variance will also be 0. So this was solved. And the next thing was I could write these two equations in a more general form, that I is equal to 10 3i, because if I is 0, this is 0. If I is 1, this is 10 to the power 3 as here. So this is also clear. Then I could also write these two equations in this general form, that if I is 1, then I is 1, this is 10 to the power 6, this is also 10 to the power 6. And when I is 0, this is totally 0, this was also totally 0. Okay, so at this point we had solved. All right, is everyone clear? Till this point we had done. All right. Adi, is everyone listening?
Yes, sir.
All right. Now the problem started arising from this part. So what E of y, he said that E of y is equal to E of Ey given I. So I also thought for a moment that what is this type of representation, how he has come to this conclusion. And actually we have a formula, but this formula is not written as such as is written here. So I will explain with respect to both the perspectives. Actually, what he wants us to know is that what is E of I? The very famous formula that E of Y can be written as, if I know the values or the probabilities of Y in terms of another random variable, let us say in terms of I. So I can very well write this expectation of Y, Y is this x minus 400 plus. Expectation of Y given I is equal to 1 times probability of I is equal to 1. Because I know that I takes either two values, 1 or 0. So expectation times probability I is equal to 1. Expectation I is equal to 0 times probability I is equal to 0. Right? This is a very famous formula, and this has been used often. You might have studied in your previous courses. That expectation can be given as follows. If you have the conditional information, so you do not have the exact information, but you have this sort of conditional information, you can apply the expectation conditional and then the given's probability. So this means that you are actually getting the expected value of x minus 400 plus when I is equal to 1 and x minus 400 plus when I is equal to 0. ये इक्वेशन सबको समझ आ गई, इसमें तो कोई हर्ज नहीं आपको. Is everyone? Okay. Now let us see what happens in the book. What is in the book? Now this equation, all right, it can also be written as follows. And this is also a normal notation. I can say E of y is actually equal to E of y given I, P of I, where I am summing over all values of y. So I is a random variable. I am summing over I all values of my random variable. Okay, which will be I all values, and hence I will be summing them all. The same thing, but here there were only two values. Here there could be more than two values. I just have to sum over all those values. Expectation of y given I, probability of y over all values that I can take. This is a general formula that is usually given in books. But now this book, this our Sheldon book, this has used this formula with respect to this notation. And the same notation actually is being used here. Meaning of Ey given I is actually this equation. All right. If you want to confirm, sir, how do you know how this is equal to this? Then you can see page 100 of the same book, equation 3.2. Let's try to go also there. I was also moving to and fro from from the previous pages and this page. Yes. So you can see here, computing expectation by condition. He has written E of x, E of the same notation. One will say, what is this type of EE? Then you can see it is actually given as follows. The same thing. This is a normal notation, but this is, I don't know, maybe this book has been, maybe this is normal for some authors, but I have never seen this. That is why it was causing a confusion. But this is a very famous notation. So the same notation I was actually telling here. You can also write it like this as follows. And it also makes sense. All right. Want to find the expectation of x, all right, expectation of x given y into probability of y. All right. This is, I think, hope it makes all sense. Now we can come back. So we'll be using this equation, which is actually this equation. For our case, this is actually this equation. Now, so this, I know is equal to y. This is also equal to y. So y given I is equal to 1, y given I 0, p is equal to I 0. All right. Let us try to solve one by one. Now, what is y given I is equal to 1? Expectation of this we have just solved here. So we have just saw that y given I is equal to 1 is equal to 1000. So I just put 1000 here. Now what is probability of I is equal to 1? Now what is I is equal to? I is equal to 1 happens when the damages cross 400. Now damages are Poisson. Probability of them crossing 400 we have just seen is equal to E minus lambda into 400. Now we know lambda is 1 over 1000. So we will get this value. So first term gets out to be this thing. Now what happens to the second term? Second term is E of y given I is equal to 0, probability of I 0. But what is E of y given I is equal to 0? We have just seen here it is actually 0. V of I given 0, 0. Because it will always be 0 once it is less than 400. Alright. This is totally 0. Hence you get this answer. And if you compare in the book, you also get this answer. 10 to the power 3 into e to the power minus point. And I know the notation is a little bit confusing, but actually he was missing those steps. So you can just 10 to the power 3 e minus 0.4, e minus 0.4, and this is the answer. हाँ जी, यहाँ तक सबको समझ आ गया?
Yes, sir.
All right, let's go further. Now the second thing was also to find the variance. Again, he has used this formula, and this formula, you know, we have seen this type of formula, but again, its notation was not that bad. This notation, this type of notation is used. Expectation of variance and variance of expectation is normally used. So first of all, we will see, is this true? How can this statement be true? Once we believe in this statement, once we see the proof of the statement, then we can just solve the statement and the answer will just come by solving this. Now before that, I will just tell you about a very logical statement, famous statement of conditional variance. All right, that is also given in the Sheldon book. And oh, it's not that visible, I think. So it is actually, I'll see my notes. It is 112. So 112 page of this same book, Sheldon, and you can see from there. But this is a very famous formula. No problem. It is saying that what is the variance of x given y? We know what is the variance of x given y. Variance of x. No, but I want variance of x given y. So it will be what? It will be actually x minus the mean given y is equal to x. Whatever y given x comes here. And the variance of x, this is the variance of x, but variance of x minus mean of x, actually hota kya hai? For x it is variance of x is equal to x minus mean whole square expectation. That is the actual formula. But here this will be x minus mean when y is given is equal to y, or capital Y is equal to y, whole square given y is equal to y. Alright, this formula also makes sense. Okay? Now you can go further. You can open up these, square power, x square plus e square of this thing minus 2x into e of this thing, x given y, little bit, and whole of bracket given y is equal to y. Then this will be e of x square given y is equal to y. This is y is equal to a mistake. You can write this as y is equal to y. Then this is e of square x y is equal to y is equal to y is already given, so this is remains the same, e of square x y given y. Then this is 2x e of x y given y, and this e also becomes, this is also already constant value, this e will go here, e of x given y given y. So 2 times e of x given y, this becomes e of square y. So this comes out to be this formula. This formula cuts from this formula. You get the famous representation that variance of x given y is equal to e of x square given y minus e of square x given y. And this also makes a lot of sense. If there was not given y, the formula would be simply e of x square minus e square of x. But once it is given, the formula of variance remains the same. Actually, you just put given y given y. There's a mistake here. This will be y is equal to y. This will also be y is equal to y. अभी समझ आ गए यहाँ तक आपको?
Yes, sir.
ठीक है, ये वेरिएंस का तो बड़ा मशहूर फॉर्मूला. Now, how can I get this formula? Now, the book has actually used
ये
this
on
one.
करना है भाई.
Any questions? If you have any questions, you can ask.
No, sir.
All right. So now this is well given, and actually we can also solve the problem with this formula. But let us go by the book. Now, book actually uses this formula. That is, variance of x is equal to E of variance and variance of E. Now, how can we get this formula? And so the proposition is given in the proposition 3.1. So you can go to this 112 page of your book. There you will find this. All right. So this formula I have given a proof. This is a famous formula. And this comes out to be this thing. This I also have shown you, just given the proof. Now we needed to get this formula. That variance of x is equal to E variance and variance E. How can we show that? So the proof is given in the book. So he says, all right, first of all, find E of variance. All right, so E of variance. So what is variance? Now we know that variance is actually equal to E of x square into E of x whole square, mean square. All right. So here instead of E of x square, you will have E of x square given y, because the condition is y. Everywhere y will come. And instead of just ex whole square, this will be E of x given y whole square. All right. Then we have this expectation. This will also go with this term. This expectation will also go with this term. So this term will remain the same with double e's. But what is this term? I'm saying that expectation of expectation y square given x. This we just saw, according to the book notation, is the same simple formula of finding the mean by this conditional. So this, in this way, when there's double, this means this y will go away. This will be just equal to E of x square. The same formula which I showed you here. This is a book representation of writing this formula as this EEYI is E of y. Right? So actual formula is written like this, but you can use this book notation. So EE means it is E of x square. All right. Then let us try to find the second term, variance of EX given y. Again, this will be E of xy given a square, E of x square. This is E of x square. All right. And this is actually E of x whole square. All right. We have just put the formula of the variance. E of x square, this is x, E of x square, minus E of, or the mean of this EXY, and that's then its whole square. All right, this is the variance formula. Again, you can see that this term and this term, so this term will remain the same, EEXY whole square will remain the same, and actually the same term here. All right, these two terms are exactly similar. and this term, which is e of y given x, and then it's e. So this will, double e xy, this will give you e of x whole square. This is e of x whole square, while this is e of x square. When you will add these two terms, this will cancel, and you will get the famous e of x square minus e of x whole square, which is actually the variance of x. This is actually the variance of x. Hence, this is proven that variance of x can be written as e of variance time variance of e. ठीक है, ये बुक वाला भी मैंने आपके सामने प्रूफ कर दिया, ये समझ आ गया सबको?
Yes, sir.
So now we can directly use this formula if you want to solve with the book case, that variance of x is e of variance and variance of e. So for our case, y was a vector, given was I. So it will be e of variance of y given I, variance of e given y given I. All right. Now just start putting the values and this will be solved. Now what is variance of y given I? We saw in the book it is given. All right. So we saw this. Values are here. All right. So variance of y given I was equal to 10 to the power 6. So I just put it here, 10 to the power 6. Expectation of 10 to the power 6, 10 to the power 6 will just go out, it is a constant. It will be e of I. And we saw what is e of I. E of I is just probability of I is equal to 1, because probability of I is equal to 0 is 0. Or because probability of I is equal to 0 is not 0, it's probability of I is equal to 0 times 0 is 0. So you know expectation of I is always equal to probability of I is equal to 1, because I is a binomial random variable, and this we have seen many times as well as in the last part of this lecture too. So E of I will be P of I given 1, which we know means the Poisson distribution greater than 400, which will be E minus lambda 400, and this comes out to be E minus 0.4. Let us see this part. Variance of 10 to the power 3i will be equal to the random variable 10 to the power 3i minus its mean. All right. So I take its square. So I can solve it also in a different way. I will solve first of all. Show here I can also do expectation of 10 to the power 3. 10 to the power 3 comes out, and then expectation of I know is equal to e minus 4i. So you can also solve it by this. Also you can solve it. Let us see the method I did in the first place. Square. So just take it square. This becomes I square 6i. All right, I square is 1 or 0, so no problem. And then square of this term will be e square 10 to the power 3i, plus then minus 2 this into this, minus 2 into 10 3i into e into 10 3i. So the I is equal to 1 is e minus 0.4. This is e 10 6i, 10 6 comes out, e of I comes in. This is also e of e square 10 to the power 3i. All right. While this will be e 2 to the power 10 to the power 3 e of I into 10 to the power 3 e of I. First term just comes here, 10 to the power 6 e of I. Now what is e of I? We just saw it is e into minus 0.4. This comes also here. Then here we have e of e square 10 to the power. This is total square. All right, the first I find e of 10 3i, and then I will take it square. So I know e of 10 3i is 10 3ei, and ei is e to the power minus 0.4. And then when I take it square, this will become 10 to the power 6, and this will become 0.4 into 2, this will become 0.8, or 0.4 into 2, like this, e of this. And the last term, e of I 2 times e of I square, but e of I is e of I minus 0.4 into 2, this will become e 0.4 into 2. Then these two terms are same, they will, because this all is constant, this will come outside I, e of 1 will just become 1. So this and this will add, this will become 2 times. Oh, sorry. This is already, we have done these additions. This is 2 times 10 to the power 6 e power minus 0.4. While this thing also comes out, this thing and this thing, you can see is same, but this is 2 to 10 to the power 6, this is 10 to the power 6, it's double negative. This will be minus 10 to the power 6 into e to the power minus 0.8. And if you see in here, in the book, this is also same thing. 2 times 10 to the power 6 e minus 0.4, because this will also come, this will come. And when this multiplies with this will be actually 0.4, 0.4 or 0.8. All right. So we have proven this with detailed, proof. If anyone has any question, he can ask before we move forward.
No, sir.
Oh, so we skipped some of the examples, and we also define this failure rate as follows. And we also gave a proof that probability that this x belongs to a very small, interval of dt, t to t plus dt, where x is greater than t, is given as follows, or you can also write it for failure rate into dt, where dt is a very small interval. This was also proven. Then we left all of this and we started the counting process. All right. So I think we have done all of this. So we have to start with definition of the Poisson process. All right, are we right? Have we done all of this? Hannah? You can see we have done all of this. So definition of the Poisson process. Now, before we define it, we have to define this big O of h and make it small O of h, a function f being small of h. So it will be small O of h provided the limit fh over h goes to 0. Remember here that h is going to 0. So this might come 1 over 0, this might go up to infinity. But if this quotient goes to this means
सर जो
हाँ जी,
सर जो प्रीवियस आपने स्किप करवाया ना, उसमें सारा हमने नहीं किया था। उसमें ये जो काउंटिंग प्रोसेस इज सेड टू बी, यहाँ से सर ये देख लिया था हमने।
ये सारा कर लिया है, काउंटिंग है ना, हमने यहाँ पे कर लिया था। हमने पॉइजन से स्टार्ट करना था। आप क्या कह रहे, कहाँ तक हुआ?
सर मैं कह रहा हूँ द अकाउंटिंग प्रोसेस इज सेड टू बी अ पॉजिटिव स्टेशनरी इंक्रीमेंट, ये वाला स्टेटमेंट यहाँ तक हमने बस किया था। ये जो सामने नजर आ रहा है सर, आपने हाईलाइट किया है, इससे पीछे पीछे तक किया था मैं।
अच्छा चलो कोई बात नहीं, ये कर लेते हैं। मेरा ख्याल ये कर लिया वैसे, चलें देख लें। तो वो कह रहा है कि काउंटिंग प्रोसेस एक तो इंडिपेंडेंट था, एक है कि स्टेशनरी इंक्रीमेंट्स क्या होंगे। तो मैंने बताया था कि स्टेशनरी इंक्रीमेंट्स आर जस्ट लाइक अ स्टेशनरी प्रोसेस, राइट एंड स्टेशनरी प्रोसेस, where you just depend on the tau, the difference of time between the two times where you have taken the autocorrelation, t into t plus tau, you just depend on tau. That is also interval of time. All right. So process will have station increments if the number of events in interval at any time is same. All right. So he says, or let us say,
सर मेरे ख्याल से इंटरवल ऑफ टाइम नहीं होगा, डिफरेंस ऑफ टाइम पे डिपेंड करेगा स्टेशनरी इंक्रीमेंट्स।
डिफरेंस ऑफ टाइम से इंटरवल आएगा ना, दोनों एक ही चीज है। जब आप स्टार्टिंग और एंड का डिफरेंस लेंगे तो इंटरवल आ जाएगा, और इंटरवल में इसको इंडिपेंडेंट होना चाहिए। ठीक है। So here he's saying that if it is, there is no rush time, number of people entering a store is same for all the times, then it will be stationary. Otherwise, if there is a rush hour, then we cannot say it will be stationary, because if you will count with it, at that rush hour, your count will be completely different with respect to the count, let us say, in the morning. Hence, it will not be a stationary increment. Similarly, I said that, for example, population of the Earth. So yes, if we say that the population of the Earth is same always, then we can say that all right, it might be stationary. But we know it is not stationary because population is ever increasing. So if I take the count of the people which are being born, then in that case, if I let us say start counting today, and then if I start counting 20 years before, it will not be a stationary count or stationary increment. Then for footballer, it will also not be same because he says that in this age a person scores greater as compared to this age. So that is why counts will be different, it will not be stationary. But you can say, let us say if I take smaller increments, that might be stationary. For example, I take increments over a month in the same age bracket, then it will come out to be same. It might be stationary then. So it all depends on the type of justification you have employed to show that whatever the counting process you have devised is a stationary process. ठीक है जी, हो गया सारा, अब आगे चल सकते हैं.
Yes, sir.
यस सर, हो गया हो गया.
हाँ, ठीक है. आप लोग इतना हंस क्यों रहे हैं? इसमें हंसने की बात है मेरे ख्याल से. ये क्या
सर आपने मेरे ख्याल में गुस्सा किया इस बात का.
नहीं, मैंने तो गुस्सा नहीं किया. मुझे लगा था मैंने पढ़ा दिया, मैंने गुस्सा नहीं किया. मैंने कहा चलो वो आप लोग थोड़ा सा ब्रेकें लगा रहे हैं मेरी गाड़ी को, मैं चलो थोड़ा दौड़ूं तेज. असल में मुझे साथ से हमने ना एक चीज हमारी रह गई, वो असल में जो होता है ना वो स्टोकेस्टिक, यानी और आप कह लें कि प्रोबेबिलिटी डिस्ट्रीब्यूशन फंक्शन ऑफ अ वेक्टर, जैसे होता है ना गॉसियन रैंडम वेक्टर होता है, उसकी हमने डिस्ट्रीब्यूशन नहीं कर सके. असल में वो हम ये ना इतना आपका कोर्स था मार्कऑफ ऑफ पॉइजन, इसमें ही लग गए और हमने सारे को काफ़ी कंडेंस कर लिया. उस कंडेंस करने में ना एक ये इंपॉर्टेंट चीज़ रह गई है कि अगर आपसे बाद में है ना PDF ऑफ वेक्टर, तो वो पार्ट हमारा रह गया. मैं देखता हूँ ये अल्लाह करे पॉइजन्स हो जाए ना, तो शायद मैं क्यूइंग से पहले ना वो वेक्टर वाला पार्ट करा दूँ आपको. देखते हैं, खैर पहले पॉइजन कर लें, चूँकि ये तो खैर मुसीबत आ गई तो इसको तो ख़त्म करना है हमें. ऑलराइट, so definition of the Poisson's process. Before we start, we can define this f of function being small o of h. What is this thing? So it is defined as this: a function is said to be o of h if f of h divided by h tends towards 0. Here remember that h is going to 0. If h is f of h is a large number, then 1 over 0, that large number, this will go up to infinity. But if f of h goes to 0 earlier than h, all right, or f of h is smaller than h, then definitely this totally will still be 0. All right. Now there are certain axioms you can well prove yourselves. So he's saying
इसमें f of h क्या है, क्या चीज किसे रिप्रेजेंट कर रहा है f of h और oh और ये मतलब
ये आपको तो शक्ल से नजर आ रहा है ना, f of h is a function of h and h is any variable whose values are going towards 0. I was just saying that from this equation it becomes actually apparent that f of h must be smaller than h, so that it goes to 0 earlier than h, and hence the overall quotient will be 0. Let us do some examples. If I say f of h is x of square, this will become h of square of x of, जो मर्जी आप h भी x भी लिख सकते हैं, आपकी मर्जी. This becomes f of h, this becomes h square, h cancels, this becomes limit h0, this tends towards 0. So this is OH function or small o of h function. Fx is equal to x square. But fx equal to x is not OH because h cancels, you have 1, and limit of 1 h tends to 0 is still 1. So this will not go towards 0. This will be not big O of h. Then it says that if they both are big O of small O of h, then their sum will also be small O of h. You can see the very simple proof.
सर ये OH क्या है?
OH क्या है? You can just assume. आपने पढ़ा हुआ है बिग O और स्मॉल O? एल्गोरिथम्स में पढ़ा है आप लोगों ने? हाँ जी, आप में से किस किसने एल्गोरिथम्स पढ़ा हुआ है? एनालिसिस ऑफ एल्गोरिथम्स पढ़ा हुआ है किसी ने आप में से?
नो सर।
नो सर।
डेटा स्ट्रक्चर्स में नहीं पढ़ा आप लोगों ने? तो आप लोगों को
No,
डेटा
sir.
स्ट्रक्चर्स पढ़ाया जाता है?
नो सर।
नो सर।
तो आप किस यूनिवर्सिटी से हैं सर?
डेटा स्ट्रक्चर एंड एल्गोरिथम पढ़ा था
सर मैं इस्लामी यूनिवर्सिटी ऑफ बहावलपुर।
अच्छा चलो ठीक है। हाँ, दूसरी मैडम जिन्होंने कहा था नहीं पढ़ा, वो कहाँ से पढ़ी हुई है?
सर मैंने पंजाब यूनिवर्सिटी से ही पढ़ा है, लेकिन 2 साल पहले पढ़ा था, तो तब ये सिलेबस में नहीं थे सब्जेक्ट्स, अब शायद हूँ।
अच्छा। और एक और कौन सी मैडम जिन्होंने कहा कि उन्होंने पढ़ा हुआ है, वो कौन सी मैडम है?
सर मैं अजीन अहमद।
अच्छा, आप कहाँ से आई हैं?
लाहौर कॉलेज फॉर वुमेन यूनिवर्सिटी।
तो आपके यहाँ पढ़ाया जाता है डेटा स्ट्रक्चर्स, एल्गोरिथम्स या एल्गोरिथम्स वगैरह समथिंग इस तरह का कोर्स?
सर पढ़ाया था, थर्ड
तो
सेमेस्टर में हमने पढ़ा था।
उसमें आपको पढ़ाया बिग ओ स्मॉल ओ कुछ पढ़ाया है?
सर रिपीट कीजिएगा, कौन सा?
बिग ओ ऑफ एच या स्मॉल ओ एल्गोरिथम्स के अंदर?
सर याद नहीं है।
अच्छा चलो ठीक है, कोई बात नहीं, थैंक यू। सो ये एक्चुअली थोड़ा बहुत वहाँ पढ़ाया भी जाता है। मैंने एक्चुअली मास्टर्स कंप्यूटर साइंस में की थी ना फास्ट से, मुझे इसका थोड़ा आइडिया भी है, इसलिए मैं आपको वहाँ पे ले सकता हूँ। मगर बहरहाल आप इसे
सर आपकी तो फील्ड होगी
क्या? नहीं, फील्ड तो मेरी कम्युनिकेशन है, मगर ये
एल्गोरिथम्स।
एल्गोरिथम से आप देखें ना
सर
हर जगह
एक्चुअली इलेक्ट्रिकल इंजीनियरिंग में इतना उसको डीपली नहीं पढ़ाते, उसमें बेसिक चीज़ें ही हमने मतलब ज़्यादा हमने नहीं पढ़ा था इतना, जो कोर्स में हमारा आउटलाइन था मेन
पता
चीज़ें ही
नहीं
हमने पढ़ी
आपको
थी।
किस बुक से पढ़ाया था उन्होंने?
सर अब मुझे नाम तो याद नहीं है बुक का।
नहीं, अब आप मास्टर्स कर रही हैं ना, तो कोशिश करें, अच्छा होता है इंसान अपनी किताबों का नाम याद रखे, ऑथर्स का नाम याद रखे। उमूमन कॉलमैन की बुक पढ़ाई जाती है, तो ये तो पहली चीज़ होती है। जब आप एल्गोरिथम्स का एनालिसिस करते हैं तो उनका यही देखना होता है कि उनका बिग ओ क्या है या उनका स्मॉल ओ क्या है। इसका मतलब होता है कि वो कंप्यूटेशनली जो उनकी कंप्यूटेशन टाइम है, एक फराज तुम स्लो कीजिए, जो उनका कंप्यूटेशन टाइम है ना, वो किस इक्वेशन से हम उसको आप समझें कि उसको बाउंड कर सकते हैं। ठीक है, बहरहाल ये बात की बात। अभी तो आप बस ये समझें कि बिग ओ ऑफ एच का मतलब ये है